What's that? Okay. I might remind me at the end of the class what it is. I'll write down the name. All right. The problem with a lot of the tools, like there's something called Screencastify, but I think it has like a 5-minute limit unless you pay for it. And I think the problem is I'm asking my computer to like do too much at once with being connected to the board. I don't know. I'm not super tech savvy. There's a really cool thing where you wear this little camera and it like tracks you around the classroom. Don't know if I want to post myself. All right, we ready to go now? Hello, hi.
Hello.
All right, so differential equations. Let me see if I can kind of scroll down to one. So these would be examples of differential equations. So like right here, this one has a couple of different derivatives in it. It has y triple prime, a third derivative, y prime, a derivative. This guy has a couple of different derivatives, an original function maybe. We're going to start solving ones later that look more like these guys, where we'll have like dy dx is sine of x. The cool part about these is we now have tools to get back from like a derivative to an original function. We have the process of taking an antiderivative. As you scrolled, you might have seen those weird things at the end. These are called slope fields. I'm going to show you some pictures that are a little bit bigger than this. The reason slope fields are kind of stupid on the AP test is they have to be really small for us to do them, but they're really only cool if they're big. So we'll look at some of these later today. But like, how cool does that look? I think it looks cool.
It looks pretty awesome.
Thanks, Herbie. So we're going to kind of just get a feel for what these could be good for by writing some differential equations, just kind of translating from English into calculus talk. So we're going to review a couple of words that you learned probably in Algebra 2. I know 2 of them get used in Algebra 1. Does anyone remember direct variation, inverse variation, joint variation? Do you remember hearing those words at all? No? Okay, cool.
Yeah.
Oh, cool. All right, so I'm going to write down some equations. These are really just kind of fun factoids that will help us write some of these things. Helps us with proportionality. So direct variation, or you might hear directly proportional, is like y equals a number, a constant. Usually we use the letter k in this class times x. The kind of, anyone have a job? That's a really good example of direct variation. So the amount you get paid y is directly proportional to the hours you work. So that constant of proportionality would be like your hourly salary. Teacher example, the grade you get on a test is usually directly proportional to the hours that you study, is the like classic teacher driven example. Varies inversely. Anyone think they know what's different about that one? What do you mean? Instead of multiply, I divide. So y equals k over x. A good example of that, the classic teacher example is the grade you get on a test is inversely proportional to the amount of time you spend on your phone during class. You could also do like ice cream sales is probably inversely proportional to, or is that directly proportional? Because hotter temperature, more ice cream. That was a terrible example. Yeah, I don't know. The amount of cold it is. There you go. All right, varies jointly just means there's multiple variables. So you could have like k, x, z. A lot of things we do don't just depend on one thing. So we'll see an example of that later. So what we're going to try to do is just translate some stuff into some differential equations. What we'll end with next time is actually an example. It's actually going to be this example. But there's going to be some word problems that we deal with. So let's see if we can translate. All right. So we're going to try to write this in math speak. It says the rate of change of b with respect to t. What have we been calling rates of change this year? What calculus thing? You only have 2 options. Is a rate of change a derivative or an integral? Anyone listening? Rate of change, aka slope, is a derivative. So the rate of change of b with respect to t is going to look like db dt. Wow. All right, is proportional. This means directly proportional, if you don't see that word, to the cube root of b. So I'm going to put my constant of proportionality and my cube root of b. Since the directions just say write a differential equation, I'm literally done. You may ask, Yo Hefty, are there any questions that are this easy on the AP test? Answer, yes. There are some that are just write the differential equation. All right, this one, the rate of change of y with respect to x. What am I going to write? dy dx, our good old friend, is directly proportional to y. I'm going to put my constant of proportionality. I'm using k and then y. Again, direct, we're just multiplying. All right, I think we're getting better at this. This one is really important. We're going to talk and solve this differential equation next time to the point where we're going to memorize the solution. It's that important. All right, the rate of change of s with respect to n. Thoughts? ds dn is proportional to the sum of s and n. I need my constant of proportionality, so I'm going to use k. And then what does the word sum mean to you? All right, so s plus n. Using those parentheses because I want to make sure that constant goes to both.
What is K?
It is our constant of proportionality. So when I say proportional, I'm not really saying like equal. I'm saying that it's a constant multiple of it. So that's helping me not say equal. It's helping me say I'm a multiple. I just don't know what that constant is yet. You could theoretically use a different letter. So if you wanted to use H for Herbie, you could.
So is that like the number?
So it's a number that we usually would solve for in the context of a question. All right, let's get a little more real worldy. The rate of change of the weight of a puppy, P, with respect to its age, A. What's the rate of change of my puppy with respect to its age? How can I write that in math? dp dA. All right, with respect to its age, is inversely proportional to the age of the puppy. Thoughts? K over A. Perfect. There was a question, I think we'll do it next class, about a puppy on the AP exam. It was very cute. All right, this one is one if you're taking BC next year. This is a type of equation that we work with a lot in BC, a whole day on it. In a group of G friends, the number X of friends that have eaten a cookie changes with respect to time at a rate that is jointly proportional to the number of friends who have eaten a cookie and to the number of friends who have not eaten a cookie. That's a lot of words. Why don't you guys take a second with your groups to try to write what you think that differential equation could be?
They're just saying what they want.
What?
You have to repeat the word.
I'm gonna take this now. Aside from that. Hair's getting a little long there, bud. What?
It was actually a lot longer than you.
I feel like you always wore a hat though.
Yeah, but it was crazy.
Yeah. What? No. Sorry. I might be able to snag a mint from the workroom during our break. Okay. All right. Does anyone know the derivative side, the rate of change side? What's that going to look like? The x dt. I like that. Anyone know anything that's going to go on this side? Whoa. Okay, that's a lot. So I like the constant of proportionality. What does x represent? Number who have eaten the cookie. And then what did you say for the last part? G minus x. Does that make sense? We got G total friends. X have eaten the cookie. So the ones that haven't, G minus x. Love it. This happens, if you're wondering, to be called a logistic differential equation? Any of you in like a biology class, if you've seen like an S-shaped curve like this, talked about words like carrying capacity, that's the differential equation that goes with that one. So just fun facts. All right. Plants. I like plants a lot. For the first 6 weeks of a plant's life, the rate of change of the plant's height increases at a rate that is inversely proportional to time t in weeks. We also see some new directions. State any domain restrictions. Anyone know what the derivative side is going to look like? I like d something, and I do like dt. dp dt. Now notice they didn't tell me with respect to time here. They didn't explicitly tell me that. But if we're talking about a rate of change of the height, that's fine. All right, inversely proportional to time t in weeks. What's that going to look like? K over t. Now, this says state any domain restrictions. Now, our domain for this one would be our t for time. What do you think we can go between? Yeah, so 6 would be our upper bound on that. What's our lower bound? 0. Should I include 0 in this domain? No. Can anyone tell me why not? No. Why no?
When you're 0, you have to.
Okay, fair. Also, look at that differential equation. Can I plug 0 into that t? No. So mathematically, I really shouldn't include that t. So that's a little bit of context on what you could use differential equations for. To be quite honest, this is probably the most real-world applicable thing we do. My sister is getting her PhD in biology, I guess would be the best statement of that. And a bunch of the papers that she looks at, I looked down one day and there was literally a logistic differential equation in it. So she uses a lot of this stuff to deal with things that change over time. So. All right, what time is it? You guys want to break already? Okay. Let's go for 4. We have 2 tasks left. So we're kind of working with 3 big tasks today. Writing, checking if something's a solution, and then slope fields. So take 4. Oh. Yeah.
Stop. Wild, that one's funny. Yeah, one. I think this one. Yeah.
All right, let's continue rolling. I have an algebra 1 question for you because it's the same question. Our solution just looks a little bit different. How could I answer this question? Is x equals 3 a solution to the equation 2x plus 1 equals 8?
No.
How do you know? All right, so I could plug in 3, right? I could do 2 times 3 plus 1 equals 8. That 6 plus 1 is 7 equals 8. No, not true. What? So I could solve the equation. Why I am not solving the equation is differential equations are actually super difficult to solve sometimes. So if we're looking back at the calculus side of this, if it'll let me, a lot of the time we're not going to be able to solve a differential equation. So though I could solve something and see if the solution is what I want, sometimes it's easier to just check by plugging in. Differential equations are kind of a huge topic to the point where some people devote their lives to trying to solve differential equations. We're going to learn how to solve literally one type. If you come back to BC, you'll kind of go a little bit more in extent there. But there are classes in college. I took a whole semester-long class called differential equations. There's another class called partial differential equations. Some people focus on that, literally spend their whole lives trying to solve differential equations. So we're going to see a very, very few amount that we can actually solve. So what we can do instead is we can try to plug in and see if something works as a solution. Now, unfortunately, our solution gets a little bit more complicated because we're not looking for a number as our solution anymore. We're looking for a function as our solution. So notice here, this guy is what we're trying to see is a solution. So we're looking for a function that has a certain relationship with some derivatives. So what we're going to do this is collect the information we need to plug in. For this differential equation, those are the two pieces of information I need to find. Y prime is our first derivative. What's y triple prime? The third derivative. So we're going to collect those derivatives. We're going to plug them in. We're going to see if we get something that's true or something that's false. As I am writing down y prime and starting to think, is there anything you want to remind me about the derivative I'm about to take? Oh, chain rule. Why chain rule there? Yep, cosine is happening to 2x. I like that. So this is our chain rule. So let's go ahead and take our derivative. What's the derivative of cosine? Negative sine of 2x. And then I'm going to multiply by what? 2. I'm going to write it like this. All right. On my way to find y triple prime, I need to find y double prime. Any claims on that?
Negative cosine.
All right. I like the negative. We're going to have a cosine. We'll still have our 2x. What will my coefficient be? What should I put there? Options I'm hearing are 2 and 4. Do I have to chain rule again? Yes. So the number that should go here is 2 times the other 2, or 4. All right. Will the third derivative be positive or negative? positive because I'm going from cosine back to sine. So I'm adding in another negative sign in the equation. What number should go here? 8. So yeah, let me write it out in a couple more steps. Probably should have. Thanks, Sadie. All right, so here I'll keep the negative 2. Derivative of sine is cosine 2x. And I'm multiplying by 2. So I have negative 4 cosine 2x. That multiplied by 2 at the end coming from our chain rule again on this. Yep, so let me write those directions. So now when I do this guy, my derivative of cosine is negative sine times another 2 for another chain rule. So those two negative signs are going to become a positive. I'll have, oh, I'm missing something. I'm missing my 4. Excuse me. That should have been a 4. Then your 4 times your 2 is your positive 8 sine 2x. All right, cool on our 3 derivatives now? We good? So what I'm going to do now is take my original differential equation, y triple prime plus 4y prime equals 0. And I'm going to plug in the things that I have. So y triple prime, instead of that, I'm going to be writing 8 sine of 2x. That's what I got for y triple prime. I'm keeping the 4. And then for y prime, what should I plug in for y prime? Yep, I'm going to choose the one with the 2 at the front personally. I know. No. I don't know. Technologically savvy and know why my computer keeps freezing like this. It's supposed to be a better computer too. But it keeps the projection. Like 2 seconds. Yeah, it was helpful though that it did that like 3 times in a row while I was getting observed. What is this? Yeah, Sadie, just go to the bathroom. Sadie, if you want to go to the bathroom, I'm arguing with this for a second. So. There we go. Cool. Anyone got any cool weekend plans? Did this freeze again? No? What's happening here? Did OneNote freeze now?
Yeah.
Aha! All right, we ready to finish out this question now that I've successfully defeated my technology? All right, so looking at this, I could simplify this back end, right? So I've got 8 sine of 2x. Last time I checked, 4 times negative 2 is negative 8 sine 2x. What's 8 sine of 2x minus 8 sine of 2x? 0. Now,
oh wait, why didn't you plug in the 8 sine? Oh wait, never mind.
So this one went here. This one went here. What do you mean? No. So what we do have to find out, this last thing, is this true all of the time, no matter what value of x? Yes. is the answer to that question. 0 is always equal to 0, no matter what value of x I plug in. So I'm going to say that this equation is a solution to that guy. Sorry, I thought I was frozen again. Like touchscreen. All right, so here's my actual answer. Y equals cosine 2x plus 7 is a solution.
You have to write the sentence.
Yes, because it's kind of the answer to the question. So it's asking if I am a solution, so that does need to be part of my answer. I'm just going to write myself a note here. This is true no matter what x is. So one thing we kind of have to change in our heads about solving equations, and the idea of solving an equation is our solution here isn't like x equals a number. Our solution here is going to be an equation. All right, let's try one more question. Then I want to hit slope fields because they're easy. I might skip this bottom. Maybe I'll let you guys do the bottom one. All right, so that was kind of boring. I don't know about you guys, but taking 3 derivatives and plugging in, not the most interesting question in the world. So let me make this question a little bit more, 1, I think interesting, and 2, a little bit more AP in style. So we want to know for what value of k will this thing be a solution to this differential equation? So if I'm looking for what thing is this a solution, I need to find these 2 things to plug in. Now notice I'm only plugging in for the y stuff, the y's, the y primes, the y double primes. I don't have to plug in for x stuff because that's not like the thing I'm solving for. I'm solving for an equation that's like y equals, so I don't have to plug in for x stuff. All right, you guys see the chain rule? I do. All right, so we're going to take a derivative of k e to the 3x. What do you think the derivative of k e to the 3x is? Times, I'm going to put my 3 there. All right. What do you think the derivative of e to the negative x is? All right. I would have to multiply by -1 for my chain rule. So I'm just going to subtract instead of add. Let's find y double prime because we need it to plug in. That is my chain rule for my negative x. It's like I multiplied it by -1 for derivative of negative x. All right, 3ke to the 3x. What is his derivative going to look like? Beautiful. 9 coming from 3 that was there times the 3 for the other chain rule. What's the back end of this going to look like? Why is it plus? We have a -1 from the first chain rule, a -1 for the second chain rule. All right, so now we're going to plug in to this differential equation over here. I'm going to do it on this side. So I've got y double prime was this 9k e to the 3x plus e to the negative x. All right, they're asking me to subtract what y was, so my original guy. So k e to the 3x plus e to the negative x. And they're saying that equals 18 e to the 3x. Whoa, this looks crazy. Looks like a lot's happening. Do you guys see anything good that's happening in this equation? Anything that might be able to cancel out? All right, let's look at these 2 terms right here. I have e to the negative x minus an e to the negative x. Do you guys agree with me and Matt that those would cancel out? What? Hold on. So we have 9k e to the 3x minus k e to the 3x. What did you say it was, Hermie? We have 9k e to the 3x minus k e to the 3x. I subtract. So what would this be? Yeah, so I need to subtract their like terms. So I have 8k k e to the 3x. All right. Stop arguing with it because I'm looking for the value of k. This is not just yes or no. So what can I do? What do you guys think we can get rid of? All right. I could divide by 8e to the 3x if I wanted to. We can divide by that whole thing. I'm allowed to divide by something with x's in it. Usually you're not supposed to do that, but e to the 3x is always positive no matter what. So we can divide those away. And we're left with k equals 18 over 8. Anyone good at reducing fractions? 9 over 4. All right, so I think this is a good example of a problem that's definitely doable, but kind of looks terrifying. We're kind of getting to that realm of calculus. Here we go. All right, I would like you guys to try one on your own. It's like the first one, though. It's the easier one, just yes or no. So you have y equals c sine of 2x. This c is a constant. Yeah, so it's like the same as k, or like if there was a 3 out there. I want you guys to try to plug into this differential equation and tell me whether it's a solution or not. I'm going to give you about 4 minutes to try. While you do that, I'm going to try to look up some pictures so I can show you how cool slope fields are before we have to do some slope field problems. So again, that constant in front is acting just like a coefficient. He can just hang out while you're taking derivatives. Slope fields.
So the C just doesn't change.
Yeah.
Yeah, no, I'm on one.
All right. Get rid of some stuff because my computer is protesting. I would like to see the images, please. I'm not even going to try to open up my Desmos things. Look how cute they are. Anyone done already? How fast can you go? Yes? Is that the answer, or you're just done?
No, that's not the answer.
It's going to show as a coefficient. Yeah, so our plus, that's kind of like our plus c. Our c can end up in weird random places when we do differential equations. Yeah. It's going to be fun next time. minutes is too long. All right, what's missing where my arrow is? A 2. Where's the 2 coming from? The chain rule. All right, for your second derivative, was it negative? Wow, what number am I missing? 4 coming from 2 times the 2. Ooh, that x is ugly. Hold on. All right, so when I plug in, I'm doing y double prime. Oops, that's not what y double prime is. Plus y prime. Plus 4y. So 4c sine of 2x. All right. I had that these the first and the last term kind of go away, and I get 2c cosine 2x. Is this true no matter what x is? No. For example, at x equals 0, this would not be true. So I just wanted to use this as just an emphasizer. A lot of people would want to like solve for x here and figure out what x is. We don't care about that. We want this final thing to be true no matter what the value of x is. So our conclusion, our actual answer, what is our actual answer? Yeah, it's not a solution. And when I say it is not a solution, I mean this function is not a solution. So sine of 2x, c sine of 2x is not a solution. All right, the last thing we're going to talk about today, I think personally, is probably the easiest thing I teach you all year. A lot of other teachers don't like it as much, but it's really just drawing a picture, and there's really defined rules for how we draw a picture. So we're going to draw and then analyze a little bit what's called a slope field. And I want to show you some pictures of some because we're not going to make ones that are really big because it's going to get really tedious. But this is the idea of kind of what a slope field does. The slope field itself is the green lines. What it's going to show us is the slope of the solution to a specific differential equation. Why these are cool is we're not really able to find a ton of solutions to differential equations. But if we put in a little bit of work, we can kind of know what one looks like without actually solving the differential equation. So these 3 graphs here would represent solutions to the differential equation that made this slope field. Now there's multiple of them because when we solve, what do we put at the end of all of our integrals? Plus c. So that plus c can give us different curves. They're called particular solutions instead of just a general solution with our plus c in it. So we can get an idea of what that would look like even if we can't solve that differential equation, because the math that goes into actually making the slope field is not very hard at all. I can have my c in different locations. So you kind of saw the c in front of the sign before. So you can get weird looking slope fields, like this would be a slope field, and look how different those particular solutions look. Absolutely. So our C's get in weird random places once we start working with these. So you can get like very strange pictures going on. Yeah. No. So I think that was graphing solutions that weren't necessarily functions. We'll be graphing ones that are functions, so pass the vertical line test, but you can get really cool kind of solutions going on depending on what your curve looks like. Now, to be fair, these can look really, really cool, but they look cool when they're big. The problem with the AP test is look how many points we're going to do. Kind of sucks because it does get a little tedious. So you're usually going to be asked to graph somewhere between 9 and 12 points. It's not very hard, but you don't get the coolness factor of it. So as we roll through, we're going to talk about some different ways we can be asked about slope fields, but actually drawing one I think is kind of the least cool option here. So I'm going to do the first one. You guys are going to do the second one. I'm pretty sure after one example, you guys are going to kind of get the feel. So what we're going to do is we're going to plug in our 9 points to find the slope at each of those points. Then we're going to try to draw a little line that has the same slope as the thing we're doing. Now, what thing on my paper represents slope? dy dx. So I'm just going to take all 9 of these points and plug them in. I'm going to draw a little line segment. Question, looking at dy dx right now, is there a description you could give of where the slope is always going to be 0? Yeah, do you see what Matt's saying? When y is 1, the slope is always going to be 0. Yeah, so what I'm going to do is I'm going to draw very flat horizontal lines everywhere y is 0, because dy dx equals 0 when y is 1. If you can see some patterns like that, you can certainly avoid having to plug in all of the points. Yeah, so this one, you would have problems at x equals 0. Notice, do I have any points on this line? No, so they won't ask us ever to do points where the slope is undefined. For the rest of them, I'm just going to plug in. Now, I'm going to show you the way I like to write my work, but really it doesn't matter. Whatever you want to do, I'm going to grade this one, and I'll talk about how I would grade that question, because I've asked a bunch of AP graders on how they would grade it. I like to write the points kind of in the order they are on my paper so I don't mess up. So I'm going to do -1, 2 and -1, 0. Purposefully writing -1, 2 on the top because that's where the point is. I've done these before where I've written it down and then done them in the wrong order. Yeah, so because I figured out that it was 0 when y equals 1, I don't have to plug in that point now. So I'm going to plug into this. I've got 2 minus 1 on the top is 1. -1 squared on the bottom is 1. 1 divided by 1, last time I checked, is 1. So now you want to think with your like algebra 1 slope brain. What did you call slope in algebra 1? 2 words, starts with R. Rise over run. So 1 is like rise 1, run 1. So what I envision the line that's kind of going through these 2 points as I draw my line segment through here. So you want to draw something kind of like that. Now, if you're like me, you might find that a little wishy-washy, because you're like, what if I draw it too steep? What if I draw it too shallow? So it doesn't have to be exact. You're going to do the best job you can. All right, if I plug in -1, 0, I get -1 on the top and I get 1 on the bottom. So I want a slope of -1. So again, I'm kind of visualizing the line that goes not like that, but through here, without that lump in it. And I'm going to try to do like that, kind of comparing to make sure the slope of the top one and the bottom one look relatively similar in steepness. All right, we're going to keep going. I'm going to plug in the ones at 1. So 1, 2 and 1, 0. Are these going to be exactly the same as the ones we just did? Yeah, it's going to be 1 and -1 again, because the only change I made was to that x that was squared before. So drawing here, kind of imagining it go through there. And yeah. All right, the last ones, I've got 2, 2 and 2, 0. So this guy is going to be 1 over 2 squared, or 1/4. This guy is going to be -1 over 2 squared, -1/4. Now, -1/4, 1/4, those are a little hard to draw. What I do want them to be is less steep than the ones I drew for 1. But I want to make sure they look like they're slanted and not like they're flat like the ones at y equals 1. So, okay. Nice. If you don't like the line that you draw, erase it. Draw another one. It's okay. You're going to notice as I draw these, I usually hate the first line I draw pretty much every single time. So what would that look like? Well, what do you, is there anything you see that you could tell about the graph? Are they all okay? Like as you move that way, they're kind of approaching one. I notice there'd probably be some sort of like horizontal asymptote at y equals 1 because all the slopes are 0 there. You can't tell too much because it's so small is the problem. So I could have something that's kind of rolling in like this maybe, but you can't really see. No. So here we're just seeing if we get the points and the slopes on the points. I'd be grading just the 9 dots here, the 9 slopes. Yeah, so let's talk about how I grade this. What do you want to focus on? There's usually, if you have to draw, and there's usually 3 points that this is worth. The first point is for the slopes that are supposed to be 0. So if you're going to focus on anything really, really hard, focus on making those 3 as flat and perfect as you possibly can. The second point usually goes for your like the sign of the slope. So do you have positive slopes where there should be positive slopes? Do you have negative slopes where there should be negative slopes? The last point is kind of the most wishy-washy. It's kind of just relative magnitudes. So does everything look like, does this look like it's about a slope of 1? Is this one less steep than that one? So it's a pretty lenient grading system. You're not going to get points off if your line's just a little bit weird. If I'm drawing this for 1, that's when I might start getting points off. All right. So not a super hard process, but definitely one that we can do. All right. I'm going to actually skip the next one. We'll warm up with that one next time. I want to go down to this guy right here because this is way cooler. And then we'll finish up. All right. So for drawing solutions to differential equations, this is the way they tend to be asking about slope fields right now instead of making you draw one. So the last time I saw a slope field on the AP exam, it was actually this question right here. We're going to practice with this one first. So here, what I'm going to be doing is drawing the kind of graph that goes through the line. Biggest thing here, this is again another one that's going to feel a little wishy-washy, but the biggest thing here is you want to make sure that you're going through that point. So I'm going to do these in 3 different colors because we're drawing 3 different things. What's your first favorite color? Green. This green or the darker green? So we're going to do, we can do one in lava. We're going to go through the one that's 2, 6. It's this point right here. So when I do this, I kind of just don't want to straight up disrespect a slope. So I'm going to follow along, but my graph is probably going to look a little different than Sadie's graph. It's going to look a little different than Laisha's graph. It's going to look a little different than Walt's graph, and that's okay. I'm going to try to follow along the slopes the best I can, trying to not just like completely disrespect them. Now, there's a flat slope here, so I'm going to kind of follow along the flat slope, kind of like it's a horizontal asymptote. We're just drawing a line that goes through the slopes here. Yep, educated guess. It's not going to be super perfect, but I see that these are going down. See, the one I'm going to draw right now is probably going to look a little bit different even. So we're just trying to follow on. Yeah, you can either try to touch them if it makes sense, go in between them if that makes sense to you. What you're really trying to avoid doing is drawing something that looks like that just like goes straight through the slopes at like a perpendicular angle. All right, let's try another one because it makes more sense the more that you do. What's a good color to go with green? Pink. All right, 4, 2. All right, 4, 2. That's this guy right here. So again, you're kind of going up. You can touch the slopes if you want, or you can kind of just follow along. You're just trying not to be super disrespectful. What do you mean? The line. You're kind of just following along. I'm going to choose to flatten out at 0. You might not have. That's okay. Now, 1, 4 is kind of the most interesting one. So what's the most interesting color you can think of? What? Lava? Okay. All right. What do you think this one's going to do? Yeah, this is going to be super flat. So this one, and they love putting this one on the AP test. That one needs to be really flat. Yep. So you can touch the lines. It's totally fine to touch the lines. You just don't want to like go through them at a weird angle. So you kind of want to follow along with them. So what we're doing is this is actually a differential equation that's really, really hard to solve. This actually matches with the cookie one we did at the very beginning. It's really hard to solve, but if we have some information, we can give a pretty educated guess as to where this function is. Let's say I only have this point. I might be able to give a pretty good idea of what it's doing at like time 6, even if I can't solve it. So you're getting a good idea of what the solution looks like without having to be able to find the solution. Or you're just drawing a really pretty picture, whichever thing you like the best. All right, I want you guys, as us kind of finishing up notes, I would love if you guys could try these two. So again, grading wise, you need to make sure you're going through the points. So there's 2 of them here. And you're kind of just not super disrespecting the slopes. I'll do mine in a couple of minutes, and then we'll do some end of class wrap up. And since I love timers, I'm going to start talking in like 3 minutes. And don't feel scared to like, yep, just draw the lines.
We can just ignore the equation.
Yeah, so for this one, we really don't need the equation at all. This would be a good example of like response question. So part 1 might be to do this with a slope field. Part 2 might be to actually solve it. Actually, I think this one was a... Let me see if I can find it. Is it this old? It can't. I feel like it's 27.
He wants to do both of them or just be on top?
Both of them. Yeah, make sure you're drawing both of the graphs. You should have 2 graphs as you go. Ah, here it is. All right, did you guys draw them both already? All right, so I'm going to show you what mine look like, and then we're going to look. I actually found this free response, so we're going to look at how they graded it. So mine, this one. Did yours look the same? Wow. All right, so I'm going to tell you my next one's probably not going to look like yours, and that's okay. Yeah. Let's see. I'm going to go up like this. Whee! Ish. And yeah.
That's exactly what I did.
Yeah. Sometimes
You could have gone straight down though, right?
no, these are flat slopes right here. We got to make sure we turn around. And then I checked earlier. I wasn't pleased. I'm not really pleased right now. This slope field itself looks really symmetrical, and my graph doesn't. So I'm gonna try again. Because of these flat slopes, I need this to flatten out right here. And if you're kind of working the other side, what? Like lower or higher? Not really. All right, so let's look at this rubric really quick. So I'm going to show you first. Here's the actual free response question that I'm working with. Oops. So notice part A is this guy that we just did. Part B was to write a tangent line and use it to approximate something. We can do that. Part C is what we're going to learn how to do next time. Here's how they graded this question. So notice theirs is a little, excuse me. Theirs is a little different, but it was 2 points and just 1 for each of these. But stop moving. Hold, please. So notice what they said. They said hers must go through the indicated point. So that's super important. Follow the given slopes. That's a little wishy-washy. And you want to make sure you extend it to the boundary of the slope field. So you want to make sure you go through the whole thing. But notice theirs doesn't look perfect. Ours, well, theirs does look perfect. But ours looks kind of similar. That's fine. I talked to a grader about this specific question. It can go lower. It can go higher. All right, so we are at the end of class. Next class is going to be a lot heavier in terms of like what we're doing in the notes. But please bring your problem set, because instead of doing a notes check, I'm going to have you go directly to your problem set to do the questions in there. If at any point you do more questions on the problem set, if you need to sticker up your problem set with correct answers, I am more than happy to do that. Thank you for your what?
How far is the problem set do you go with what we've done?
Just anything that says solve the differential equation, don't do that. All right, thank you guys so much for your hard work today. I will see you next week. Have a great weekend. Thank you, too, Matt. All right, now I get to teach an entire semester's worth of calculus.